Hey guys, it's Henry. We're going to be solving this problem. It's a nice little conservation of momentum, conservation of energy problem. So first off, let's read it. Gail runs at a speed of 4 meters per second and dives on a sled. Initially, it rests on the top of a frictionless snow-covered hill. After she has descended a vertical distance of 5 meters, her brother, initially at rest, hops on her back and they continue down the hill together. What is the speed at the bottom of the hill? The total vertical drop is 15 meters. And then we got the givens. So let's start our problem by doing a diagram, right? So we gotta get my pen. We have Gail. Let's call that G. Let's have a G, and she's going 4 meters per second towards a sled going 0 meters per second. And the problem implies there's like a little hill right here, so let's draw the hill. After she has descended a vertical distance of 5 meters, so that means that before Gail's brother gets on the sled, she's going to descend 5 meters, so let's call that 5 meters. So that is before the collision. Now we need to draw our after the collision. So this, in case you haven't noticed, is a perfectly inelastic because Gail is going to get on the sled. So after that, we're going to have a single dot still on top of the hill. That's a terrible hill, but let's go with it. And it's actually going to be of mass G plus S. And we're going to find the, let's call it V2. Or 3, since we're going to call that V2. So let's start off with the easy part. Conservation of momentum. So the momentum at the beginning is going to be the same as the momentum at the end. Also, from just our equations, we know T equals mv, mass times velocity, and the sum of all the momentums is going to be the sum of all mv's. I'll hide this. So let's get started with the problem. We have to get the momentum at the beginning of the before the collision. So we're gonna have mg, that scale, times her velocity, and then we're gonna have the sled times its velocity. We're gonna have the final momentum. It's gonna be Gail v3, and this is gonna be perfectly inelastic. We're gonna have two v3s. We can just factor out or distribute. I'm not sure which one it is. The v3 from both of them because they have that in common. Now we divide through. Okay, now we can plug into our calculator, but first we can do a little inferring. So the velocity of the sled is going to be 0, right? So we can get rid of that, and it's going to be that's going to be the velocity of Gail and the slide. So mass of Gail is 50. Right here it says it. Times her speed, which is 4 meters per second. Let's call mg right there. And ms equals 5. And mb equals 30. That's good enough for me. So we're going to have mass of Gail, 50 times 4 meters per second over the sum of the masses. It's 200 divided by 55. We're going to come out to 3.64 meters per second equals V3, or the velocity before Gail goes down the slide. So I'm going to so we know from this that v3 equals 3.64, and that's before she goes down the slide and have 5 meters there. So I'm just going to copy the problem again and put it at the bottom so we can follow it. What did I do? I don't know. There, got it again. So we have found the velocity before. Okay, so second part of this problem, after she has this inner vertical distance, her brother, who is initially at rest, hops on her back. So we need to find the velocity before her brother hops on her back. So we have the mass of Gale and the slide, and it's going to head down the hill. And we know that before Gale's brother gets on her, it's going to be 5 meters, and they're going to reach this point right here. So we need to find the velocity at this point. That's going to be v4. Okay, so from this, we need to know our conservation of mechanical energy. And we know that the mechanical energy is going to be the kinetic energy plus the potential energy. That's going to be equal to both of them at the end. So kinetic energy is equal to 1/2 mv. The initial velocity is going to be 3, and we're going to square that. That's the equation. Plus mgh, let's call it I. The distance at the top of the hill is going to be I, so 5 meters. Then 1/2 mv4 squared, that's the one we're trying to find, plus mgh f. So what we need to do is isolate the equation so we get v4. So let's go ahead and do that. Actually, before we can actually divide through by the m, we don't need it, and multiply by 2 as well to get rid of the halves. So we're going to have v3 squared 2ghi equals v4 squared 2ghf. And before we even do anything else, we know that we can assign a variable to h right here. As it's going to be at the bottom of the hill right here, we just call it 0 and get rid of that term. That's way easier. So now we have v3 squared plus 2ghi equals v4 squared. Now it's an easy problem. Just get the square root of this. So when she gets down, they're going to be at this point, v4. We can plug into our calculators, or, I guess I'll write it down. 3.64 meters per second squared plus 2 times 9.8 meters per second squared. That's not squared. The whole thing squared. Sorry. See, second squared times the height, and it's going to be at the top, so 5 meters. Let's just span that all the way. Some parentheses, and that's going to be our velocity when Gale gets to the point before her brother gets on that sled. So 3.64 squared plus 2 times 9.8 times 5. And then get the square root of that. And so her velocity is going to be about 10.55 meters per second before her brother gets on the slide. So let's copy I have it already. So let's just count again. We're gonna, okay, so now we're gonna have another collision, another inelastic collision. Hold on a second.